So you can write on your worksheet for this. Obviously, I'll get to 6, Nate. I will get to your question, but I want to talk about all these. Using the discriminant. Now, first things first, this will be an easy flashcard, but I'm adding it. I'm adding 2 flashcards that I'll re-upload this weekend. The I cycle, the 4 that you have to memorize. I is I squared is -1, I cubed is -I, and I to the 4th is 1, and also the discriminant, okay, which we're going to talk more about today. B squared minus 4AC is the discriminant, and that's a vocab word I've mentioned in class already, but we're going to look more into it. So in 4, really, you don't know how to do this yet. Determine whether each of the following quadratics has real or imaginary zeros. Maybe you do. We talked about it yesterday. What causes imaginary numbers? What'd you say, Andrew? A negative under the radical. So if your discriminant is negative, you're going to get imaginary zeros. So regardless of that portion, we could have calculated the discriminant for all of these, right? Andrew, can you just fly through and tell me what you got for your discriminant value for all of these? Okay, so if I'm looking at all those discriminant, these 3 with a negative discriminant, a negative value under the square root sign, those are all going to give you 2 imaginary roots, okay? 2 imaginary ones. If your discriminant is positive, that would be A and C, that's going to give you 2 real roots, okay? And we'll look more into that in a minute. And if you get a 0 discriminant, you're going to get only 1 real root. So we will talk about those more today. In number 5, it mentions the discriminant again. Which of the following, if graph, would lie entirely above the x-axis? When you solve equations, you're solving for where the graph crosses the x-axis. If it never crosses the x-axis, that's because you have imaginary solutions, right? If you get solutions of 3 and 5, it will cross at 3 and 5. If you get solutions at 4, it will cross at 4. If you get imaginary solutions, it's never going to cross. So which one of these has the imaginary solutions, and it tells you to try to use the discriminant to figure it out versus doing the whole quadratic formula 4 different times, right? Because all we need is what kind of discriminant? Negative. So which one of these had a negative discriminant? Working backwards, option 3, if I look. B squared is 16 minus 4 times A times C. 16 minus 28, sure enough, is -12. So that has the negative discriminant, which means that graph is only going to hit it, or is never going to hit the x-axis. If I go back up to these positive discriminants, they're going to hit the x-axis twice. You're going to get 2 solutions. You're going to get 2 solutions. This one, if you get a discriminant of 0, I said you're going to have 1 solution. How would the parabola have to hit the x-axis in order to get only 1 solution? Nate? Nope. Say it, Bo. Lydia, what were you going to say? No, not side. We're not going to do sideways parabolas other than kind of when we wrote with a focused directrix, because they're not functions. Maggie, what were you going to say? It doesn't have to be the if that was the root, if that was the answer you got, it would hit the origin. But these aren't the roots. This is just the discriminant. This just is the discriminant. This is just the value underneath the square root. So we're going to have some number, think quadratic formula, plus or minus the square root of 0 all over 2a, which is going to be some other number. So this isn't our answer. This is just the discriminant. But think about it. If you take a number and add 0, what are you going to get? Just that number. If you take the number and subtract 0, what are you going to get? That number. So you're going to get the same answer twice. So you're really only going to get one solution, hence this. But what that looks like is really, Bo said, the vertex. The vertex, the only way to get one solution is for the vertex to be hitting the x-axis and then going back up. Okay, because if it hits it twice, it hits it once on the way down and once on the way back up. If it hits it, if it never hits it, well then it's just never going to hit it. But if you get one solution, that one solution has to be at the vertex, where it just kind of hits the x-axis and bounces back up. Okay? And that's because a discriminant is 0. We get one solution because when we add the 0 versus subtracting the 0, you get the same answer twice. So it's really only one answer. Does that make sense? Okay? So now and this is kind of the way one of the ways discriminants will be tested. For what values of C will this have no real zeros? And if you have no real zeros, that means you have imaginary ones, right? So what does the discriminant have to be? Again, John? Negative. So your b squared minus 4ac, how do you say in an inequality that it has to be negative? Negative numbers are numbers that are less than 0. So we want our discriminant to be negative. We want our discriminant to be less than 0. So given that we know b is 6 squared minus 4 times, given that we know a is 1 times c, we want to know when this is less than 0. So we just have to solve this. This is going to be 36 minus 4c is less than 0. And what do I do to both sides to solve this? How do I get c all by itself? Subtract the 36, so negative 4c is less than negative 36. Then what? Divide by negative 4. A little alarm should be going off in your head. Because in an inequality, if you divide both sides by a negative number, what do you have to remember to do? Flip the sign. So it's going to be c is greater than 9. Does that make sense? Yeah. So let's take a peek here. This is just going to help us. So if c is greater than 9, let me go with 10. Look, just watch up at the board and sit back, relax, think about this. I made the c greater than 9, so supposedly this is going to have no solutions. Do you agree? Never hitting the x-axis. If I go back and I make that actually equal to 9, what do you think is going to happen? It was plus 10. What happens if you take a function and subtract 1 off of it? What does it do to it? Shifts it down 1, right? So where this used to be, which had no solutions, now the whole thing, if I make it a plus 9 instead of a plus 10, the whole thing is just going to shift down 1 unit, and now it's going to hit the x-axis. Delete 9. Now it's going to just hit it the 1 time, right? And if I make my c value less than 9, if I subtract 1 more, this graph is going to shift down 1 more, right? So my c value being less than 9 at 8 is now going to have 2 solutions. See what's happening there? So there's a little bit of transformation that should make sense to you based on shifting up and down by 1 each time. 9 is the cutoff, because exactly when c is 9, what's my discriminant going to be? 6 squared minus 4 times 1 times 9. My discriminant's going to be 0, hence the reason I have exactly 1 solution. So when the discriminant is 9, I have exactly 1 solution. If it's greater, did I say my discriminant is 9? I'm talking too fast. When my c value is 9, I have a discriminant of 0, which means I have exactly 1 solution. If I increase my c value, I'm shifting this graph up, so I have no solutions. But if I decrease my C value, I'm moving this down, and I will always have two solutions anytime I move it down. Okay? So that C value of 9 is sort of the cutoff, where we have exactly one root. Anything above, we have no roots, no real, 2 imaginary, and anything below, we have 2 real. Okay? All right. Anything else on your homework? Other than those 3, obviously. Yeah, Meg. McKenna. B on the front. E on the front. E on the front. What'd you do first? Good. So did you get x squared minus 2x plus 17? Okay. And if a quadratic is not factorable, we use the formula. So what did your quadratic formula look like? What was your opposite of b? Plus or minus the square root. Can you save me some time and just tell me what your discriminant was? What'd you get underneath your radical? That's your mistake. B squared is what? 4 minus 4 times an A of 1 times a C of 17. How did you get 13? Because I'm getting that to be negative 64. You did what? That should still 4 minus 4 times 1 times 17 should still give you negative 64. You forgot to put this 4 there? Gotcha, okay. And that's a big piece of it, is calculator use. More times than not, people know the concept. It's just a calculator mistake. Okay, other questions? All right, pass that forward. Okay, so this front side has 4 cases of the discriminant, okay? And so I've already gone ahead on case A, or part A and B, case 1 and case 2, and I've already just calculated the discriminant for us. So for part A, just put 49, and for part B, put 8. Now those are both positive numbers, yes? So they're both going to, if you have think about the quadratic formula, negative b plus or minus the square root. If you have a positive number under your radical, what does that mean? How many roots? 2, okay? Because we're going to have a number plus the number and a number minus the number, and that's going to give 2 different answers. Both divided by 2a is going to give you 2 different answers. So in both cases, we're going to have 2 roots. 2 real roots. 2 real roots. Actually, that's the number and the nature. I should have put that over here. 2 real roots. Okay? The only difference between these cases is that think about, and I'm just going to make up a b value. Think about 5 plus or minus the square root of 49 over 2, I'm making that up, versus 5 plus or minus the square root of 8 over 2. A discriminant of 49 versus a discriminant of 8. What's the difference between the square root of 49 versus the square root of 8? 49 is a perfect square, therefore when we take the square root of it, it's going to be just an integer, right? It's going to be a quote-unquote nice number. Versus when I take the square root of 8, that's going to be a not nice number. It's going to be a crazy decimal. What am I getting at? What's the difference between a nice number versus a not nice number? You know the math word? Right. Rational because the square root of 49 is just 7, versus irrational. And irrational numbers are ones that have a crazy, unpredictable decimal. So if I typed in on my calculator square root of 8, I get this decimal that's not predictable. 2.828427125. No one has any educated guess as to what that next decimal is going to be, right? Because there's no pattern. So if you see no pattern in a decimal, it's irrational. And square roots of non-perfect squares are going to do that to us. So the only difference between these are both positive discriminants. They both give us 2 real roots. It's just this one is going to be 2 real rational, and this one's going to be 2 real but irrational. So in both cases, our parabola will hit twice. In both cases, the parabola will hit twice. These will be at rational nice numbers. These will be at irrational numbers. Okay, the value of the discriminant and the value of the roots aren't the same thing, right? The only thing the value of the discriminant does for us is helps us predict how many times it's going to hit the x-axis, because how many answers are we going to have, and what kind of answers are they. In case 3, okay, our discriminant is going to equal 0. Just trust that I'm doing b squared minus 4ac and I get 0. Okay? So what happens is we get the opposite of b, which is 10, plus or minus the square root of 0 all over 2a in this case is 2 times 1 is just 2. So if we actually come up with what our roots are, what's 10 plus the square root of 0? 10 divided by 2 is 5. And then what's 10 minus the square root of 0? 10 divided by 2 is 5. So we get the same real answer twice. So this root of 5 is technically called a double root. Okay, and that's going to be an idea that's going to become more and more prominent as we move forward into polynomial functions that are bigger than parabolas, bigger than a degree of 2. If you get the same root twice, it's called a double root. Okay, and what happens, as we've seen, is that when you get a double root, and this one's at 5, it hits and bounces off. So the number of root, when we have a discriminant of 0, we have 1 real root. So 1 is the number and real is the nature. And is the square root of 0, is that a perfect square? Is 0 a perfect square? When I do the square root of 0, am I going to get a nice rational number or a not nice irrational number? Nice, right? Okay, so that's rational. And it's just called a double root, I want you to write down. You get the same root twice, it's a double root. And visually, it bounces off the x-axis. It doesn't go through and then come back around. It just bounces off of it. Okay? And the last case, which is kind of piggybacking on our imaginary numbers, this one has a discriminant of, oh boy, what was it? Let me do it quickly. B squared 64 minus 4 times 1 times 20. Negative 16. So, of course, if we have a negative discriminant, we now know we have 2 imaginary roots. And in the imaginary world, we don't talk about rational versus irrational. There's no such thing. Only real numbers kind of qualify as being rational or irrational. That's not something that we talk about in imaginary. But we can see our 2 roots. So if we actually go and find them, the opposite of b is 8, plus or minus the square root of the discriminant we said was negative 16, all over 2. That gives us 8 plus or minus 4i over 2, which is 4 plus or minus 2i. So we can see our two roots. One of them is 4 plus 2i, and the other one is 4 minus 2i. And because of that, our parabola never hits the x-axis. Okay, we have two imaginary roots, two imaginary zeros, two imaginary x-intercepts, I guess you could say. And what do you notice about these two imaginary roots that I may or may not have mentioned over the past couple days? What are they to each other? Conjugates. Imaginary roots always come in pairs of conjugates. You can't just have one imaginary root. They always, because of the plus minus, they always come in pairs of conjugates. Okay? Now, this was actually on a Regents. Which equation has 1 minus I as a solution? Now, you could just do the quadratic formula 4 times and wait and see. But I don't want to do the quadratic formula 4 times because that's a lot of work for 2 points, right? So we would use, and the shortcut would be, if you know the solutions are imaginary, right? Search for a negative discriminant, right? Imaginary solutions pairs with a negative discriminant. So now I only need to calculate the discriminant 4 times. You with me? So on number 1, and you can just watch up here, what's b squared? 4 minus 4 times an a of 1 times a c of negative 2. That's a positive discriminant, so I need to go no further. Get rid of that one. It's not going to have an imaginary answer. On number 2, b squared is also 4. Minus 4 times an a of 1 times a c of 2. That's a negative discriminant, so I'm going to keep that in the mix. D equals negative 4. The next one, b squared is still 4. Minus 4 times a times the c of negative 2. That has a discriminant of 12, so don't talk about it. And number 4, b squared is 4 still. Minus 4 times a of 1 times the c of 2. That's a negative discriminant. So at least I've boiled it down. Now I only need to do the quadratic formula twice. So the opposite of b here is negative 2, plus or minus the square root of, I already did the discriminant, it's already negative 4, all over 2a in this case is just 2. So when I simplify this, the square root of negative 4 becomes 2i, and then everything is divisible by 2, so negative 1 plus or minus I. Is that the answer? Is 1 minus I a solution? Is that 1 minus I? No, it's negative 1 minus I and negative 1 plus I, but not 1. So I think by default we could say 4 is the answer, but just to confirm. 2 plus or minus the square root of negative 4 all over 2 is going to be 2 plus or minus 2I over 2, which is going to be 1 plus or minus I. Is 1 minus I one of those solutions? Yes. Okay? So their purpose there was to see if you knew how the discriminant could really, I think what they were getting at is using the discriminant to make it a shortcut. No one wants to do the quadratic formula 4 times only for 2 points. It's a lot of work. Okay. Let's go to exercises 5, 6, and 7. This is going to be similar to what was on your homework last night. For what values of a, so you're going to be finding the value of a, will this not cross the x-axis? Okay? Kaylee M., what do you know about parabolas that don't cross the x-axis? If they don't cross the x-axis, meaning they look like this, what's imaginary? The roots are imaginary, but what do you know about the discriminant, most importantly? The discriminant is, if you have imaginary solutions, your discriminant is what kind of a number? Negative. Very good. So all we're going to do here is we're going to take the numbers that we do know and make it negative, negative being less than 0. So b squared is, let me write this, b squared minus 4ac needs to be less than 0, needs to be negative. B squared is, what number? 16. Minus 4 times the a that we don't know, and the c is 2. And we need to solve the inequality. So at first I'm going to clean this up to 16 minus 8a is less than 0. Are we all good with that? And solve it just like we did on last night's homework. Subtract your 16 over. So negative 8a is less than negative 16. And divide both sides by negative 8. So what's my answer? Connor. A is, what's sign? Right, we divided by a negative. A is greater than 2. So for what values of A will the parabola not cross the x-axis? And if you wanted to check that, let's put in an A greater than 2. 3x squared, and then the rest of it is this plus 4x plus 2. And look at a graph of that. Do we agree that that does not cross the x-axis? What do you think an A of 2 would do? Exactly 2. You think it would hit? Perfect. And what do you think an A of less than 2 would do? Right. So you can't really wrap your head around that via transformations as well as the other model that we saw, but 2 is the cutoff. Right at 2, it's going to hit it once. Greater than 2, it hits it no time. Less than 2, it hits it twice. Okay? Same question, but just what's the value of B? So we're missing our B that will intersect the x-axis exactly once. What do you know about the discriminant here if it hits it exactly once? It's exactly 0 if it hits it once. So we need to set our b squared minus 4ac exactly equal to 0. We don't know b squared. Minus 4, we do know a is 1 and c is 25. So that's going to be b squared minus 100 equals 0. Add 100 to both sides, so b squared equals 100. And so what's the value of b? There's 2 values of b. Plus or minus 10. So there's 2 different scenarios here. So again, for confirmation, I'm going to type in x squared. I'll check the positive 10 first. Plus 10x plus 25. You can graph that. Agreed? And also, I'll try the minus 10. Oh, I don't want to use negative. Totally different parabola, different location, but still hits it once. Let me make one connection for you on this one, because this is, if I have B, look up at the board, being plus or minus 10, what does that make the trinomial? Let's make it the positive 10, for example. This trinomial is a what? Perfect square. Remember that half of b is 5, squared is 25? And it's a perfect square of x plus 5 squared. So if I were to tee that up, x plus 5 equals 0, and the other x plus 5 equals 0, where are my x-intercepts? Twice at negative 5. It's a double root. See that? And hence it hit the x-axis exactly once. Just a connection to be made to help you fully understand a lot of the stuff that's interconnected. So your homework's coming out, and you have a spiral you can